Good afternoon, buenas tardes. My name is Giovanna Gennard, Assistant VP for Public Relations at Old Dominion University, and I'm joined by Raul Briceño, Associate Professor of Physics and Staff Scientist at Jefferson Lab. As co-chairs, we, along with our dedicated planning team, would like to welcome you, our more than 11,000 registrants from more than 135 countries, to the Remote Experience for Young Engineers and Scientists program known as REYES. REYES is a virtual program that, as physicist Ann Nelson once said, really attempts to maximally exploit the talents of a great humanity. Our goal is to expose as many diverse young minds as possible to science, to technology, engineering, math, and health science by making science more inclusive and accessible. And to accomplish this goal, we invite outstanding contributors to science and technology from ODU and other partner institutions like NASA, Jefferson Lab, University of California, Berkeley, and more to share their knowledge freely with all of you. You're the next generation that is going to fuel future science and technology breakthroughs, and that's why this program is so meaningful to us. So this year's summer program starts today and runs through August 19th. It will include more than a dozen free virtual sessions, along with a growing virtual mentoring program that pairs students interested in working on a research project with field experts and scientists. All of our sessions will be broadcast live on Zoom and on YouTube, and the majority will also be recorded and made available on the ODU REYES YouTube channel, because we want to make sure that you have an opportunity to watch them and rewatch them at any time. And now I leave you with my co-chair, Raul Briceño, who will introduce us to our distinguished keynote speaker, Wick Haxton. Take it away, Raul.
All right. Thank you so much, Joa, for that nice introduction. So it's a real pleasure to introduce Wick Haxton. I first met and learned about Wick when I was a grad student at the University of Washington. At that time, he was faculty there. He later on moved to Berkeley. Since then, I've had the pleasure to know him well. And I have to say that this, beyond just being a great physicist, he's also a wonderful person to interact with. And he's very much invested in supporting young aspiring scientists. And this is why it was a no-brainer to invite him to be our keynote speaker for the summer REYES program. And I was really excited when he accepted. Wick started his career by getting a double major in math and physics from UC Santa Cruz in 1971. He then got his PhD from Stanford in 1976, working on phenomena that is closely related to what he's going to tell us about today. So I'll let him discuss this physics. After that, he worked in a couple of research positions, including being an Oppenheimer Fellow in Los Alamos National Lab. After some time, he eventually became faculty at the University of Washington, where he served as the first director for the National Institute for Nuclear Theory, the INT, for an impressive tenure of 15 years. He later left University of Washington to join UC Berkeley, and he's now a joint staff scientist at Lawrence Berkeley National Lab. He has an impressive long list of recognitions and has served in numerous leadership roles. Most recently, he's now the director of a new NSF Physics Frontier Center called the Network in Neutrino Nuclear Physics and Astrophysics and Symmetries, N3AS for short. So without further ado, it's a real pleasure having Wick come join us, and I will let him take it on from here. So please take it away, Wick. You should be able to share your screen now.
Okay.
All right.
Okay.
Thanks.
Well, thanks. It's a great pleasure to be here. Raul, thanks so much for the kind introduction. I chose this problem to discuss because it's been the favorite topic in my career. I've come back to it over and over again. It's interesting historically and how it developed. I think it gives a really good feel for how science sometimes starts off slowly and then picks up momentum when new things are measured and people start thinking about interpreting them. So I'll tell you a little bit about the sort of historical development of the solar neutrino problem, which was a big deal when I was a student. And that's what first attracted me to this problem. We knew that there was an issue, but didn't know what its resolution might be. And it led to the discovery of neutrino mass and mixing. Those are topics today that really dominate a lot of what we do in both particle and nuclear physics. And the problem's not over. It has some puzzles in it that are intriguing us today. And at the very end, I'll tell you a little bit about the solar metallicity problem and what it might tell us about the early origins of our favorite star, the sun. So let me see if I can remove this. Yeah, in the Chlorine Experiment at Homestake, in 1964, the Homestake mine, which is it was actually the most famous mine in the US in terms of where most mining technology was developed. That gold mine became host to a really extraordinary experiment. It was the first attempt to prove that our nearest star produces its energy by thermonuclear fusion in its central core. And it used neutrinos. Neutrinos are very weakly interacting particles that are produced as a byproduct of the fusion process. Because they interact weakly, they come directly to us from the solar core. And so if we can measure these neutrinos precisely enough, we can actually tell in detail how the sun is producing its energy. Ray persuaded the Homestake Corporation to help him build this detector. And it was really a difficult goal. He had to bring something on the order of half a kiloton of chlorine-bearing cleaning fluid underground. And in that huge tank, he had to be able to measure about 1 event per day. He could do this because of some really interesting chemistry that allows you to extract the product of the reaction, the neutrino reaction on chlorine, which is an atom of argon. Argon's a noble gas, and so it can be easily extracted from large quantities of organic fluid by simply filtering gas through the detector. Most of the construction of the detector was actually done by the miners. They had to break this detector down that you see here into small pieces to bring it down on the hoist. And then after the containment vessel was welded together, 10 railway carloads of fluid that were brought to Leeds, South Dakota, where the mine is located, had to be brought underground in small batches. So it took a long time to do the construction. The experiment continued for 35 years, and Ray was famous for getting the wrong answer. We thought we understood how many neutrinos were coming from the sun because we knew how much energy it was producing, but he got 1/3 the result that we expected. And many years later, decades later, he won the Nobel Prize for discovering neutrino mass. The basis of what he was trying to test is called the standard solar model, but it's actually much more general than that. It's the theory that we write down to describe about 70% of the stars in the Milky Way. These are the stars that generate their energy by burning hydrogen into helium. So we wanted to test that model to see if if its predictions were in fact correct. And one of the easiest, most direct tests were to measure the neutrino production. The model itself is relatively simple. The input physics is relatively simple. It assumes that the star burns in local hydrostatic equilibrium. So that means there's a balance at every point in the star between the gas pressure gradient, the gas is the electron gas in the star, and the gravitational force. It assumes a mechanism for producing energy, and that's the conversion of 4 protons into an alpha particle that produces about 25 MeV per reaction. You have to model how energy is transported because you have to get energy out of the core to the surface and then eventually to us. And the energy is transported in the interior of hydrogen burning stars by radiative transfer and in the envelope by convection. And then we know a lot about our favorite star. We know lots of boundary conditions. We know the mass, the radius, the luminosity. We know the depth, the convective zone from measurements that we can make. And so all of that input information is put into the standard solar model. And then we have to put a lot of theory to actually build this model. The electron gas has an equation of state, and we need to describe that. It's pretty close to a simple kinetic gas. We have to produce cross sections for many very low energy nuclear reactions that are important to solar fusion. And that's taken decades of very careful measurements in laboratories. We have to describe how radiation moves through the star, and that's the so-called radiative opacity. The specific atomic species that are in the sun at various radii are important in controlling that opacity. So that's a detailed atomic problem. And we have to have some means of fixing the initial composition of the sun. How do we start integrating the differential equations describing this physics? What's our boundary condition? And one of the most important variable in this is the ratio of hydrogen to helium to metals. Astronomers call anything above helium a metal. And so these three parts of the composition are important because they have a big influence on issues like the radiative opacity. And as I said, this model is, in fact, the model that describes about 70% of the stars in the Milky Way. Now, when Ray first started developing his technology, he did it in smaller detectors that he used at reactor sources of neutrinos. He didn't think about initially applying this to solar neutrinos because of the fact that the neutrinos that were produced by the sun, at least prior to 1959, were thought to be very low energy. And they were actually too low in energy to generate the chlorine to argon transition that Ray was interested in seeing. So prior to 1959, there was not much motivation for trying to attempt a really large experiment. But in 1959, there was a measurement in the laboratory of the reaction of helium-3 plus helium-4 that's shown here. If you can see my cursor, I don't know. I guess I can't see it, so you can't either. But the helium-3 plus helium-4 producing beryllium-7 turned out had been underestimated by about a factor of 1,000. And that result increased the branching ratio to two other parts of the PP chain. So the PP chain is the name we give for this production of 4 protons into helium-4. And in fact, there are 3 pathways through this chain to produce the final product of helium and to generate the 26 MeV of energy that comes through that cycle. So what's interesting about this pattern, that once you begin to realize that the sun has multiple pathways for converting hydrogen into helium, is first of all that each of those pathways is actually connected with a neutrino. The neutrinos are produced every time there's a weak interaction, an interaction that changes a proton into a neutron. And so if you can measure the neutrinos, you can actually tell at a given instant how the sun is producing its energy. Which fraction is going through the PP1 cycle on the left, how much is that going through the PP2 cycle in the middle, how much is going through the PP3 cycle on the right. So that's exciting. The other thing you notice is that because the reactions, the center of the sun, although it's very hot, still the temperatures are very low on nuclear scales. And so reactions between charged particles are inhibited by their Coulomb repulsion. And this becomes more and more important as you involve heavier species. So the result of that is quite a startling dependence on temperature. The PP chain goes like the 4th power of the core temperature of the sun. The PP2 chain goes like the 11th power. The PP3 chain goes like the 22nd power. And so that ratio is very, very steep. And so what you've learned is that if you actually can measure the neutrinos, you have a thermometer for measuring the core temperature to a precision of actually better than 1%. So that was Ray's goal, was to try to verify, first of all, that the sun is producing energy by this PP chain. And second, to use that energy production and this pattern of neutrino fluxes to determine the core temperature to this very precise value. And in fact, those 3 neutrino species have different spectra. So what's shown here is the flux of the neutrinos at the Earth as a function of the energy of the neutrino. And what you see is at the high energy N, There are these boron-8 neutrinos that extend up to about 15 MeV and have a pretty good flux. And those were the neutrinos that Rey was primarily interested in measuring because his detector was suitable for those neutrinos. That detector, by the way, itself has had a history because the original idea that chlorine to argon, that transition, might be a really attractive way to measure neutrinos was suggested by a theorist, the Russian theorist Pontokorvo. And then this idea was taken on by Louis Alvarez at Berkeley, who spent a couple of years thinking about how to do an experiment. In the end, he was interested in a different application and didn't go forward with an experiment. But then Rey took over the idea and developed it into a practical detector that he could use both at reactors and in looking for neutrinos from the sun. Later on, we found a second way. Why the neutrinos are so important is that they allow us to look inside of a star. That is a kind of a generic property of neutrinos. We can't see what's going on in the interesting part of the star where the energy is created, except through these very weakly interacting particles like neutrinos. But some years later, we began to develop another tool to probe deep inside the sun. And that's the idea of helioseismology. The sun actually vibrates. In fact, if you look at the surface of the sun, the most important modes go up and down about every 5 minutes, and they have an amplitude of about 30 meters. And so from that fluctuation, you can actually measure through the Doppler shift associated with that this fluctuation is occurring. In fact, there are many other modes. So if you do very, very careful studies of the surface of the sun, Doppler studies, over very long periods of time, you can recreate many of these modes and then do a Fourier analysis to determine how the modes propagate in the center, in the deeper parts of the sun. And this Fourier analysis essentially measures the sound speed as a function of radius in the sun. So helioseismology became another way of probing deep into the interior by just looking at this almost earthquake-like physics associated with these fluctuations. So this was some pictures from the old days of the experiment that was done. Why the experiment was so intriguing was that it was a wonderful partnership that formed between Rey, who's shown on the right here with his hand on the detector, and John Bacall, who was a young theorist brought into this problem very early on when Willie Fowler at Caltech realized that solar neutrinos might be measurable. And Rey and John had a lifelong friendship where they worked together on this problem. John doing the theory of the standard solar model and on anything else that was relevant to the solar neutrino problem, and Rey doing the measurements. What was really interesting about the chlorine experiment, it was so far ahead of its time that when the result was achieved, 1/3 the expected result, there was no way of cross-checking it. And so I would say that most of the community thought that this is an extremely difficult experiment. Rey did really well to get within a factor of 3 of the right answer. It's probably just a bug in the experiment somewhere, some systematic. He would patiently explain for the next 2 decades all the cross-checks he made that very unlikely. However, it took 2 more decades before technology arose that was sufficient to actually to measure some other portion of this solar neutrino flux. So Rey's experiment was sensitive to these, primarily to these high energy neutrinos. A bit later, we took a proton decay detector that was built in Japan, the Camioca detector, and redid its electronics to allow it to measure much lower energy events. It succeeded finally 20 years later in measuring neutrinos as well, and they wound up with a result that was actually consistent with Rey. So that was the first verification, but it took 20 years to get to that. And then there was a third experiment, very much like Rey's experiment, radiochemical. That is, you look at the neutrinos, the neutrinos pass through a detector, they produce a product, the product accumulates, and then at some point we flush the detector and measure that product to determine the net flux. That was the gallium and sage experiments that used a material called gallium, which was particularly interesting because it had a very low threshold. So it could see not only the high energy neutrinos, but in particular, the lowest energy neutrinos, the PP neutrinos that dominate the solar neutrino flux. And when those 3 results were put together, something very curious happened. And this is shown on this graph. In theory, there are lots of parameters in the sun. In fact, when you build the model, there are about 20 pre-parameters that have to be measured independently. They all have uncertainties, and they have to be put into the model to determine solar properties. But when it comes to neutrinos, actually only one thing matters. No matter what you change, what is important is the core temperature. The core temperature essentially controls the flux of solar neutrinos that are being produced. And so that tells you that no matter what you do to the physics, if you were to plot the neutrino fluxes as a function of the core temperature, they must have some regular behavior. That regular behavior is shown here with this line. At the very top where you see all the dots, that's actually the solar model with all of its parameters change according to its their believed uncertainties, and there's not very much variation possible. The other dots and dashes correspond to what we would call non-standard models, models that make usually some unjustified conjecture to try to solve the solar neutrino problem. And some of those models do produce lower fluxes of neutrinos, but when you look at the ratio of the boron-8 neutrinos to the beryllium-7 neutrinos, they always follow a characteristic curve that's determined by the temperature. And where the data lay was on the left, far away from that curve. So it became apparent at this time, which was about 1990, that there was nothing one could really do with the standard solar model to reproduce the data. The data were just different from any plausible variation that we could achieve in the standard solar model. And that got a lot of people to think about first doing much larger, much more expensive experiments to try to find out what the source of this problem was, and number two, of thinking about theory ideas that could explain what was being seen. And so there were several amazing experiments then undertaken. One of these is the Sudbury Neutrino Observatory. It had a profound effect on this problem. It used about $500 million worth of heavy water. So water where the hydrogen is replaced by deuterium. And that replacement allows one to measure 3 different reactions. Neutrinos scattering off electrons, neutrinos scattering off the deuteron and breaking it up into 2 protons and an electron, or neutrinos scattering off a deuteron and breaking it up into a neutron and proton through neutral currents. And those 3 neutrinos, three reactions, what's special about them is that they are sensitive not only to electron neutrinos. Electron neutrinos were the only neutrinos Ray Davis could see, and they're supposed to be the only neutrinos that are produced by the sun. These are also sensitive to muon neutrinos and tau neutrinos, the other 2 families of neutrinos that exist in the standard solar model. So this detector was built because of the possibility that the electron neutrinos that were produced in the sun somehow managed to change before they got to Earth, change and hide themselves in a different flavor. Likewise, the Camioca experiment that was the first to verify REYES experiment, a much larger version of that was built by the Japanese, involving 50 kilotons of ultra pure water to do a really high precision measurement of the high energy boron-8 neutrinos that Ray saw. This experiment was mounted in the Camioca mine in Japan. And third was Boroxino, which is a relatively small detector, but it consisted of the purest scintillator that we've ever created on Earth. It was mounted in the Italian laboratory at Gran Sasso, a tunnel, inside of a tunnel. Its very low threshold allows you to make a map and measure neutrinos event by event from the lowest energy to the highest energy. So it's a very ambitious experiment. This is a result from the SNOW experiment. It shows these 3 bands correspond to the 3 detection channels I showed you. And what's plotted is the flux in electron neutrinos versus the flux in mu neutrinos, how those 3 bands would change. And you see that there's an intersection there with the circles around. That's the measurement that came from these combining these 3 measurements in SNOW. And what it tells you is that roughly 1/3 of the neutrinos that are arriving on Earth are electron neutrinos, and 2/3 of them are mu and tau neutrinos. So indeed, Ray actually got the right answer. He measured the correct number of electron neutrinos arriving on Earth, but the other neutrinos that were predicted by a model had transmuted into muon and tau neutrinos, evading detection in his detector, but they could be seen in the Sudbury Neutrino Observatory. And this requires, if these neutrinos change, requires something new that was not in the standard model. And that is that neutrinos, instead of being massless like a photon, have to have a mass. And they also have to mix. What this means is that if you think about this in just sort of simple 2x2 quantum mechanics, and we'll simplify to just 2 neutrino flavors. If we have an electron flavor and a muon flavor neutrino, what we mean by that is that those are the eigenstates, neutrino eigenstates of the weak interaction. So the weak interaction produces either a new E or a new mu. But in that same 2x2 space, there's another basis that you can imagine. Those are the neutrinos of definite mass. We'll call them nu1 and nu2. And the neutrinos of definite mass are, once you produce a neutrino and you let it propagate through free space, it's the mass that determines how they propagate in time. And so these two representations of neutrinos don't necessarily have to be coincident. There can be a non-trivial angle between them. So the electron neutrino can be a sum of the 2 mass eigenstates and vice versa. And if you just go ahead and do the quantum mechanics of that, assume that the electron neutrino and the muon neutrino are some mixture of the 2 mass eigenstates. That's usually described by this at the bottom here, this mixing angle theta 1, 2. There's some cosine and sine amplitude to describe the mixture of the nu E in terms of the nu1 and nu2. If you just explore that and ask what happens as a function of time, you find out that neutrinos oscillate. So if you produce a neutrino at a point in time and then watch it, measure it downstream, you'll find it, if it has amplitude 1 at time t equal to 0 where you produced it, later on you'll find out that it has the amplitude less, has a probability of less than 1, then it comes back and restores again. That's shown here with this graph. This is a little calculation with a particular mixing angle, and it shows you if you measure the survival probability, what's the probability as a function of distance away from the detector of measuring a neutrino, then it oscillates back and forth like this. But it turns out, and this was a really an intimate part of the solar neutrino problem, that this vacuum oscillations that we knew about in the 1990s, it in fact is much more interesting when you do look at the same phenomena within a star. And that's because if you're familiar with the notion that when a photon of light goes through water, its velocity changes because it interacts with the medium. That's the source of the index of refraction you see when light tends to bend when it goes in water. That's why it's hard to pick up a penny when you drop it in a pool. That same effect that you acquire a different mass when you're in a medium also occurs for neutrinos. And it occurs because the neutrinos scatter off the material around them. In particular, on the left, you show that nu E and nu mu both scatter off the electrons through neutral currents. So because they both scatter off that, it doesn't really change anything. They both acquire the same contribution to their mass from that effect. But on the right, there's a diagram that allows a solar electron neutrino, because there's an electron neutrino, to scatter through charge interactions off the electron. And that's a diagram that only contributes to the electron neutrino scattering and not to the muon scattering. And furthermore, if you calculate the sign of this in the standard model tells you this amplitude, it turns out to be positive. What that means is that when electron neutrinos go into a medium, they act as if they're heavier than they are when they're in vacuum. And this has a really interesting implication that's shown here. If you just put in this physics and redo your calculation, you find out in vacuum, you get what you get on the left. And there's an oscillation, but the electron neutrino is mostly electron neutrino all the time. If you go to the right and you go into matter, you find out that there is a very dramatic change. A neutrino that starts off an electron neutrino can emerge from the sun, mostly a muon neutrino. And this it's actually a familiar problem that you may have seen in atomic physics. It's how a spin acts in a magnetic field when it has an up and down direction, and you start to change the direction of the magnetic field. In the neutrino, if you start in vacuum, and that's on the right here, the electron neutrino is very light. But as you increase the amount of matter, go deeper and deeper into the sun, it gets heavier and heavier. So there's a possibility that there's enough matter in the sun that the electron neutrino actually becomes heavier than the muon neutrino and crosses at that point, causing this level crossing. So this kind of level crossing problem in quantum mechanics is, again, studied in many different contexts. We know what happens. This particular problem doesn't start on the left at the vacuum. We start instead in the core of the sun at very high density, and then we watch what happens as the neutrino propagates out of the sun. So if it starts on the right, on the left here, where the neutrino is actually the heavy neutrino, and propagate, one of two things can occur. First of all, that's the crossing point. That transition can be, if you start on the electron neutrino, the heavy mass eigenstate at very high density, and then follow along gently, you just stay on that same quantum mechanical trajectory and you exit the sun, and you can see what that does. It takes an electron neutrino and converts it into a muon neutrino. And that is if this transition is adiabatic. What that actually means is that the oscillation length of the neutrino, when it goes up and down every oscillation, the density changes only very moderately within an oscillation length. So the neutrino can't actually tell that the density is changing. It's just changing too slowly for it to notice. So it continues to propagate in the normal way, but adiabatically it changes from one flavor to another. The other possibility is that that doesn't happen, and the changes of the density in the sun are more abrupt. In that case, it's non-adiabatic. The electron neutrino jumps to the other up to the other trajectory when it hits that non-adiabatic crossing point and remains an electron neutrino. So this gets into some detail, but you can just go ahead and calculate and find out what happens. And it turns out that you have to have two conditions for this strong conversion of solar neutrinos from electron type into a muon type to occur. There has to be a level crossing. There has to be enough mass in the sun to make the electron neutrino heavier than the muon neutrino, and it has to be adiabatic. So that means that you have to be below the top line and above the diagonal line for strong transitions to occur. Furthermore, Ray didn't see zero neutrinos. He saw some. So it means you must live on the boundary, because some of the neutrinos must remain electron neutrinos, but most of them must convert to a muon neutrino. So you can just play a game and ask yourself, well, what can we do to make us find a solution? Well, the solutions always have to be like this. They have to be on a boundary. And it turns out when you then compare in detail with the fluxes that were measured, you found the solution. The solution is this so-called no level crossing. It's always adiabatic, and it just depends on whether or not the electron neutrino has a crossing somewhere in the sun. And for very low energy neutrinos, there is no crossing. It turns out the relevant parameter is the difference in the squares of the masses divided by the energy. So it becomes a big number when the energy is very small, but the high energy neutrinos are adiabatic. And so this meant that the boron-8 neutrinos that Ray was measuring were suppressed more strongly than the low energy neutrinos that the gallium experiment, for example, saw. And there's actually even more physics in this, because it tells you even about the ordering of the mass eigenstates. You can imagine two scenarios where the electron on the left, where the electron neutrino is primarily M1, the light neutrino, and the muon neutrino is primarily M2. If that happens and the electron neutrino becomes heavier, then the difference between the two mass eigenstates, M1 squared minus M2, becomes smaller in matter, and you can get a crossing. But if you're on the right and the nu E is the heavy neutrino and the nu mu is the light neutrino, then by making the electron neutrino still heavier, you're never going to create a crossing. So in fact, we learned that the order of the mass eigenstates is as on the left here, which is the only thing we actually know about the order of neutrino eigenstates today. And this beautiful physics was verified by this third experiment, Orsino, after decades of effort. They measured the PP neutrino, they measured the intermediate energy neutrinos from beryllium-7 and PEP, and they measured the boron-8 neutrinos. And just as predicted in that MSW Mikhail-Smirnov mechanism, Smirnov-Wolfenstein mechanism I just described, the boron-8 neutrinos are much more suppressed than the PP neutrinos. So it verified this prediction of theory, and in fact established not only that oscillations, that neutrinos are massive and have oscillations, but also that the particular ordering of the mass eigenstates all came from solar neutrinos. And there's kind of a neat way to think about this. This graph comes from Hitoshi Murayama, one of my colleagues. And there's been a great deal of interest, of course, about how mass is generated in general in the standard model. And all the other fermions that we know about and the quarks acquire their mass because of the Higgs. And so it's very exciting that about a decade ago, the Higgs was discovered. And what that means is that you scatter off this field that pervades all of space, converting electron neutrino, a left-handed electron to a right-handed neutrino, electron back to a left-handed chi, and so forth. It turns out that this Higgs mechanism, though, is really interesting because it can apply only if the particle being described in this way is distinct from its antiparticle. And that's clearly the case for the electron or for the muon, because those are charged particles, so the antiparticle has to have a different charge. The neutrino is really curious. The neutrino has no charge or any other what we call additive quantum number that we can assign to it. So it's not clear that it necessarily has a distinct antiparticle. And what that means is in the standard models, you have more freedom to describe its mass than you have for the other fermions, because other fermions are constrained by this condition of having a distinct antiparticle. So it could be that the neutrino is just like the other fermions, or it could be different because it has another way of generating its masses. Why this is intriguing is that if you look at the pattern of fermion masses, it's pretty strange. We now know neutrinos have a mass, but the mass is very, very light. So there's a huge gap between those the neutrino masses and the masses of the electron, the muon, and the quarks. So why is this? There has to be some reason for that. And the fact that you have these two descriptions of mass are really provide a really elegant solution. The other way, a neutrino, because it doesn't necessarily have a distinct antiparticle, it doesn't have to be what we call a Dirac particle, can be instead a Majorana particle, involves scattering to some high energy scale and scattering back down again to take a left-handed neutrino to a left-handed neutrino in our world. And when you follow that through and ask what it predicts about the mass, it's shown on the right here that the light neutrino mass is proportional to the Dirac mass. That's the mass that's characteristic of all the other particles in the standard model, times a parameter. And the parameter is the ratio of the Dirac mass to this new right-handed scale that enters because of the scattering up beyond the standard model back down again. This is called the seesaw mechanism. So if you know something about neutrino masses, you can plug in here and try to figure out what is this scale, this new scale beyond the standard model that we're measuring. That was the very first thing theorists did when the discovery of neutrino mass was announced. Turns out that the right-handed scale is about 10 to the 16 GeV. That's a very interesting scale in particle physics. This is a so-called grand unified scale where all the fundamental forces are supposed to unify and have the similar strength. So very excited. So I'm almost done here, but let me just tell you a little bit about the fact this problem just keeps giving. So we solved the solar neutrino problem. We've gone back and then done reactor experiments to see oscillations. You probably know that Fermilab is building a huge new experiment to try to see oscillations over very long distances, actually to determine that for one of the major reasons to determine the ordering of another pair of neutrino mass eigenstates. And the Japanese are doing the same. But while we've done all this, we keep working on the standard solar model and testing our understanding of neutrinos that are produced by the sun. And now we have a problem because we started to do things better, and everything that agrees so beautifully when this problem was resolved was no longer agrees so well. And the problem is called the solar abundance problem. And it just states the following: we can measure the sun's metallicity. And this is one of the inputs into the standard solar model in two places and in two ways. And the measurements now appear to disagree. One is we just measure the metallicity directly in the photosphere, because carbon, for example, if there's an atomic state of carbon, it emits a photon, we can look at that line and interpret it and deduce how much carbon is in the atmosphere of the sun. And that's a very direct and should be very reliable way of doing this determination. Or we can do it indirectly. I mentioned this theory of helioseismology before, which measures the sound speed, but the sound speed is very, very sensitive to the composition. So that gives you another measurement. It measures the metallicity in a different place in the sun, which is in the interior. And these two answers now appear to disagree by about 25%, which causes problems both in their predictions of the neutrino fluxes and other things, especially the fact that the helioseismology has to be right really constrains one. And so this has, most folks would hope that one of these measurements somehow is wrong and we'll figure out what's going on. It could be something subtle, like maybe we have another mistake somewhere, like an incorrect understanding of opacities. But so far, both measurements are holding up. In the standard solar model, the reason that we think that the sun has to be homogeneous, that's why this is a problem, comes from the fact that when it formed from a gas cloud, that gas cloud was highly convective. It went through a phase called the Hayashi phase. And because of the Hayashi phase mixing, if there were any inhomogeneities in the gas cloud, they would have been evened out through that convective mixing. So the sun must have formed as a uniform ball of gas. And so the interior metallicity must correspond to the surface metallicity. But these two metallicities, if you build models depending on using one input or another input, they disagree in their neutrino flux predictions, but somehow the neutrinos sort of are sitting right in the middle of these two models, but the helioseismology is really discrepant. So the helioseismology, you can measure the sound speed to 1/2 of 1%, but now you wind up with 1 or 2% deviations depending on where you look in the sun in the sound speed. And likewise, properties like the convective depth of the surface of the sun that we also know very, very well turn out to be wrong if you use this lower metallicity that comes from the recent analysis of the photosphere. So what's interesting about this is that maybe both measurements are correct. And if both measurements are correct, that means that something must have happened after the Hayashi phase to redistribute metals somehow in the sun. And what could that be? Is there any such event? And there is one event, and it's an event where a planet is formed. When the sun was 95% formed, almost all of the gas was already in the sun. The remaining 5% of the gas forms into a protoplanetary disk. It still contains most of the angular momentum. And there's that process of forming the planets actually scrubs out of that last 5% of gas a tremendous amount of metal. If you do the calculation, you find out there's something on the order of an excess of 90 Earth masses of metal that were incorporated into the gaseous giants by this process of planetary formation. So that means that this gas, this last 5% of the gas, once the metals are extracted, it basically must consist of just hydrogen and helium. So if that hydrogen and helium then made its way to the surface of the sun at the appropriate time, the time when the solar core was already formed, and in this rather thin convective envelope that contains about 2% of the sun by mass, there'd be enough depleted gas dumped onto the surface of the sun that surface region, the convective zone, could be diluted. So the numbers work out for this scenario. And it's really interesting. We've learned in the last 15, 20 years with various missions to Saturn and Jupiter that in fact the planets are these gaseous giants are quite enriched in the most important elements for the sun, elements like nitrogen and carbon. And so this is kind of a cartoon of how this might go, that this planet forming region has most of the ice and the dust that contain the metals sits in the midplane of this disk. That's where the planets form, and as they go around, they spiral in and they sweep out the materials, just like that late night TV automatic vacuum cleaners would clean up things as they come spiraling around. And so that extracts this, and then you see this pure gas is what actually winds up feeding onto the sun at this late stage. And when we suggested this about 10 years ago, there were some pretty good evidence that this was not a crazy idea. One is that it's been known for a long time that Jupiter's composition in detail is consistent with a scenario where 2/3 of the hydrogen that initially belonged to Jupiter was lost through the sun. And it was also known that the sun, when you compare it and other solar twins, these are stars in the Milky Way that seem to look identical to the sun, that they all seem to have an anomalous surface abundance compared to other stars that do not have planets. Specifically, if a star is similar to our sun and has planets, then the ratio of the refractory elements to the volatile elements differ by about 20% systematically. But more recently, it's gotten much more interesting. The Gaia observations of early solar systems that look very much like the sun have found huge depletions in the carbon that's being accreted onto these stars. These are complete depletions of at least a factor of 10, and they range up to factors of 40. And the first realistic theoretical modeling of these accretion disks have been built, and they find the same physics, the same chemistry, that in fact carbon is essentially all extracted from the gas stream before that gas actually reaches the sun. So let me just skip on here. And what's really interesting about this is that solar neutrinos may again actually help you determine this. The problem about using helioseismology to prove that the sun has a higher metallicity content in the core is it's such an indirect inference, and it can be influenced by things like uncertainties in the opacity. So is there a way to measure the metals in the sun directly? And there is. It turns out that there's a second branch of solar neutrinos that involves carbon, nitrogen, and oxygen kind of processing for protons. This is called the CNO cycle. And those neutrinos were actually measured just about 2 years ago by Boraxino for the first time. Very small detector, very difficult measurement, but they made the first measurement of these neutrinos. If you look at the ratio of the CNO neutrinos to the boron-8 neutrinos, which we've already very precisely measured, it turns out that ratio is linearly dependent on the metallicity of the core. And that's because carbon and nitrogen has to be there to allow the CNO cycle to operate. So this means that you can measure this one branch of neutrinos, the CNO cycle neutrinos, precisely enough, you can deduce the amount of heavy elements in the sun directly. And that was the feasibility was that again demonstrated just 2 years ago by Boraxino, and the experimentalists have looked at what they'd have to do the kind of measurement that would definitively determine the metallicity to the accuracy we need. And that requires a detector that's about 10 times larger, about a kiloton. What's exciting about that is there's a place and there's a group now trying to mount up an experiment to do precisely that. That's in this fabulous laboratory that China has built called the Jinping Laboratory. It's tremendously deep, which helps this experiment greatly. It's 2 kilometers deep. It's built as part of a hydroelectric project that the Chinese designed to provide clean energy to Shanghai. And the experiment that they're proposing to do at that depth involves 2 kilotons of scintillator. So this might be something that's done over the next decade and would actually tell us what the metallicity of the core is. And if we can establish that there's a correlation between the chemistry of the surface of a star and whether or not it hosts planets, that's a really big deal in terms of searching for exoplanets and otherwise learning more about solar systems like the Milky Way. So my summary here is that the solar neutrino problem was arguably the first demonstration of the power of what we call multi-messenger astrophysics, where you needed to know a whole lot of details about the thing you were studying, from measuring photons, measuring surface oscillations, and measuring the neutrinos to put it all together to learn something important about the inner workings of the star. And while standard solar model predictions on input parameters, the nice thing about that model is because of all these measurements, all of those inputs have specific uncertainties that can be propagated forward. So I knew when Ray measured 1/3 the right answer that was not compatible with the standard solar model. So this led to the discovery of neutrino mass, and of course, that discovery is still driving a lot of the big Fermilab scale experiments that we do today. But as the solar metallicity problem illustrates, there's still a lot of discovery potential in solar neutrinos, including this possibility of using them as a probe of the early history of our sun. And the great thing about solar neutrinos is they're free. We just have to build detectors to measure them. So thanks very much for your attention.
All right. Thank you so much, Wick, for such a nice talk. We already have several questions people have put on the chat, but let me just encourage others to write questions if they may want. And maybe before I start reading some of the questions, I think there's already some good ones. I want to also let students know some of you are joining REYES for the first time. Some of you maybe haven't seen some of the concepts in nuclear physics that have been touched. I just want to remind you that we're going to have a series of talks, introductory talks on nuclear physics under the Nuclear Physics Mentoring Program. These are going to be accessible to all of you that are participating this Thursday. And some of the basics that may be useful for you to understand some of the concepts that have been presented will be covered. And so I would encourage you to join us and then come back and watch the talk again, since this is recorded. But let me touch on there's already a long list of great questions. Let me start with the second one that I'm reading, which is, how certain are we of knowing the origin of neutrinos that are detected? Meaning, how confident are we, or how do we know that a neutrino is coming from the sun versus other sources? That's
a great question. That was the terrific achievement that came from Super Camioca, because Super Camioca, the detection mechanism it uses, a neutrino scatters off an electron. And when it does that, the electron goes in the original direction of the neutrino. So it scatters away from the sun. So after years of measurement, Super Camioca actually used their data, since they could correlate it with measurements in real time. They could correlate with the position of the sun. They could actually create an image of the sun in neutrinos, a photograph from the neutrinos. So that's the most definitive demonstration that these neutrinos do indeed come from the sun.
Great. All right. So let me go to the first question, which is about surface vibrations. You touched on solar vibrations. And the question is, are the solar surface vibrations related to visual phenomena like sunspots, or are these different phenomena?
Yeah, they're different phenomena. The sunspots are really complicated because they're probably driven by the magnetic field properties of the sun. And I would say that our understanding of that whole field is still somewhat murky. We know that magnetic flux can be confined to very, very tight spots, but we don't know in detail how it happens. We're still studying this problem intently. There was a marvelous new probe called the Parker probe that went in just to study the near solar features of magnetic fields and sunspots and so forth over the past few years. The acoustic oscillations basically have to do these major, most important oscillations that tell us the depth of the convective zone are really acoustic oscillations that propagate in that surface layer of the sun. And so that tells us how deep that surface layer is, just like a water wave in the ocean can be interpreted in terms of the depth of the water. So that 5-minute solar oscillation is terribly important for us because it tells us the boundary between the convective zone and the radiative zone. But it's really just an acoustic phenomena in the convective zone, and not really, at least as far as we know, not terribly strongly influenced by the magnetic fields that do govern solar spots, sunspots.
Yeah, interesting. So the next question is from Joseph, who's asking, what does it mean for a photon to acquire mass in water? So, I mean, this concept that, in medium can affect the mass of a particle. Can you maybe explain that?
Yeah, it's called an effective mass. It's kind of a common thing if you have a particle traveling through a medium and it scatters elastically off that, you would think maybe nothing happens, but it does. That scattering actually acts like a potential. So that potential in quantum mechanics is very similar to a mass. So if you actually measure a photon going through water, you'll find is not moving at the speed of light anymore. It's moving more slowly. And that's because it actually has acquired this mass from the fact that photon can scatter off of the water as it's propagating through. So the neutrino example is just the same, except that instead of being electromagnetic, its interactions with the surrounding medium are weak. But because the neutrino masses are so small, that very weak interaction can still influence the mass on the scale of its vacuum mass, and that's why we have this really interesting phenomena of this level crossing called the MSW mechanism.
Yeah, and I mean, these pictures that you showed from Hitoshi, I think did a really nice job of illustrating this, pictorially, right? You have the particle kind of bouncing back and forth, and so the trajectory, the time that it takes traveling across just takes that much longer, looking like an effective mass. Great. So we have a question from Alex saying, it looks like you implemented the standard solar model through Monte Carlo simulation. Can you elaborate on the Monte Carlo methods?
Yeah, so this was something actually done fairly late in the solar neutrino problem, but became very influential. It was a program that John Bacall and I think Aldo Serenelli first did. When the computers got fast enough, you could run the solar model not just once, but many times. And we knew that there were all these input, really these 20 parameters that could be varied. And we had pretty good guesses about what the reasonable variations of those were. And so literally, they just ran something on the order of 1,000 solar models, throwing the dice each time to sort of randomly distribute those input variables according to their normal distributions, and then to look at the output that came from that. I think something even better could be done today, but really hasn't been since this work is mostly 10, 15 years old now. But yeah, it was a direct Monte Carlo calculation of the standard solar model. And then once you've got those data points, you put an ellipse around it to determine sort of the 1 sigma and 2 sigma regions of plausibility.
Yeah, maybe related to this, I mean, you touched on some of the parameters that are needed, and maybe we don't have time to go through all of them, but can you maybe give us some physical intuition for what other, what are the other inputs that are needed?
Yeah, so one we've struggled with, a set that we struggled with for many years, and we still try to improve. In fact, we're having a meeting here just in a month to one more time go through this and try to define what the errors are. But it's all the nuclear cross sections that have to be measured and put into the model. Often the cross sections themselves cannot be measured at the relevant energies, and that's because the sun is actually a very, very slow reactor compared to a terrestrial fusion reactor of the sort that we're trying to design at places like Princeton and in Europe. It operates at a factor of 10 lower temperature. And that has a huge influence on how much below the Coulomb barriers these reactions take place. So when we go to measure those in the laboratory, their measurements are generally made at much higher energies and have to be extrapolated to the energies of interest, and that entails a certain amount of uncertainty.
Yeah, I mean, it's kind of crazy to think that the sun is relatively cool compared to terrestrial.
Well, just to quantify that, if you take about a cubic meter of the core of the sun and ask how much energy it's producing, it's only about a factor of 5 more energy than my bicycle light. So it's really a really slow reactor. It just produces all this energy because it's huge.
Compared to your what?
The light on my bicycle.
Okay. That's amazing. Okay, maybe let's go to the next question. So we have a question saying, Dr. Haxton, what is the rough scale over which solar neutrinos oscillate? Is the observed oscillation determined by the distance from the source, or does it have to become a superposition of the three flavors over sufficient distance.
Yeah. So in vacuum, it's pretty simple. Then there's a oscillation length, and it is dependent on the difference between the two masses that correspond to the two mass eigenstates that are involved in making up the electron neutrino. So it's literally proportional to m1 squared minus m2 squared. So the smaller that mass difference, the longer the oscillation length. So it's in an inverse relationship. In the sun, it's different because then you can make the neutrinos more degenerate. You can even cause this crossing to occur. So you find that the oscillation length in matter actually varies. And so at this crossing point where basically the vacuum mass difference between the two species is made up by the effective mass of the electron neutrino, that oscillation length is very, very large. And if you think about this and go back and this question of adiabatic or non-adiabatic, when you have a long oscillation length, that's when you can see whether the density in the sun is changing or not. So this adiabatic condition is really a condition all about this crossing point where the oscillation length gets very large.
Yeah, interesting. So we have another question. Okay, so how is the temperature related with the production of the neutrinos? Yeah,
so it varies. Really, what it does is it determines how easily certain nuclear reactions can occur. These reactions always occur. Most of these reactions occur what are called below threshold, which means that if you just thought about it classically, the two particles would never get close enough to actually interact. And it's only through the quantum mechanical process of tunneling that allows two nuclei to come close enough so that they can fuse. But that tunneling probability is exponentially suppressed, and that exponential depends on the ratio of how big that Coulomb barrier is to what the energy of the particles are. So that's where the temperature comes in. The temperature determines the energies of the particles. Basically, 3 times the temperature is the kinetic energy of the incoming particle. And so reactions that produce in the PP1 cycle, where it's only protons and deuterium and helium-3 interacting with one another, then it's relatively insensitive to temperature. But when you go to the boron-8 neutrinos, where you have nuclei like beryllium-7 with much larger Coulomb barriers because they have larger charges, then they become acutely sensitive to temperature. And so as you saw, that varied from something on the order of the 20th power of temperature down to the 4th power of temperature. When we actually build the solar model, we always require that we produce the photon luminosity. And so if we do adjust the temperature, then we have to dial something else to produce the luminosity in the appropriate way. So, but basically the different neutrino species, they fluctuate really, really radically as a function of temperature. And in fact, the solar temperature has changed over the ages. When the sun first started burning, it was about 30% cooler in its core than it is today. And this is called the early sun problem, because we really don't understand why that very cold core did not influence the biology and geology on the Earth. There must be some way that the Earth compensated for this lower luminosity that occurred at that point. But the boron-8 neutrinos that Ray Davis measured really were not important a billion years ago. The sun is 5 billion years old, but when it was age 4 billion, it produced almost no boron-8 neutrinos. Only when it reached 5 billion years did the temperature rise to the point that the boron-8 neutrinos became important.
Okay, so we're going to pivot a little bit, but you mentioned the fact that neutrinos may be Majorana particles. Can you tell us a little bit about the experiments that are trying to confirm or rule out this possibility?
That's a pretty advanced question, but it has to do with determining whether or not a neutrino is identical to its antiparticle or orthogonal to its antiparticle. And again, we don't know of any charge or anything else we can add to a neutrino to decide that issue one way or the other. So the experiment that's done today, there are actually a number of experiments that are being done and are about to scale up to a much larger size. Is called double beta decay. It turns out if the neutrino has a mass and is identical to its antiparticle, then it's possible for a nucleus of charge Z to decay into another nucleus of charge Z plus 2, so 2 higher units of 2 more protons in that nucleus, while spitting out just 2 electrons and no neutrinos. And so if that process produces 2 electrons, so it violates lepton number. So the violation of lepton number that you need, lepton number is what would distinguish a neutrino from an antineutrino. That violation of lepton number, if seen in that experiment, would indicate that the neutrino must be a Majorana particle. And so that's what's being done today. These are incredibly difficult experiments. This would be the rarest process ever measured if it's seen. And so far, lifetimes of about 10 to the 21 years have been 10 to the 22, 10 to the 23 years have been established in this game, but we haven't been able to see any neutrinoless double beta decay. So that's the experiment that's done, and there's a bunch of really good descriptions of this process on Wikipedia and so forth that will tell you more details.
Yeah, I mean, this is a hot topic of research in these fields. So I have a few questions that maybe let me try to summarize them in my own words. One of them is you present this problem, right? And I think there's many motivations for understanding neutrino physics within the realm of physics. Is there any applications that go beyond physics that may stem to other fields of science, perhaps? And then the second related question is, what can neutrinos tell us about supernovas? Can they tell us about either predicting them, or can they tell us about what happens in these supernova reactions or later on? So the first one is just general, like, does neutrinos have any other applications beyond physics, and then what they can tell us about supernovas?
Yeah, they may. Certainly, in terms of science applications, the example of this connection with exoplanets is one. If no one would have thought that neutrinos had anything to do with exoplanets. But now that we understand that this metallicity issue is an important issue in forming planets because they eat so much of the metals in these very young solar systems, if we can establish a connection with neutrinos and test that in our sun, that certainly helps us make progress on that problem. Neutrinos have been considered for some practical applications. The one that's probably being explored most readily right now is the use of neutrinos in non-proliferation. If someone has a reactor, some country that is involved in a treaty, and you want to verify that the reactor is operating in a particular way, a non-invasive way of making that verification is to measure neutrinos. So there's some serious efforts underway right now to develop detector technologies for the antineutrinos that come from reactors that would allow you to characterize a reactor without actually having to have any direct access to the site where the reactor is. So the US government is certainly funding things of this sort. So it's sort of a practical application of neutrino physics.
Yeah, I mean, that would be absolutely a great application. Are there estimates of the size of those detectors for that to be efficient?
Yeah, and some of my colleagues at both here at Berkeley and Livermore are involved in one collaboration to try to develop that technology. It's not easy to quantify, of course. It depends on how close you are to the detector, what size you need. But the fluxes of neutrinos from a reactor are actually quite a bit higher than from the sun. So they don't have to be hugely, if you have relatively nearby access, they don't have to be enormously large to be successful. The other half of the question was about supernovae, and that's a huge topic in the center that we have here at Berkeley now, because the flavor physics of neutrinos in the core of the sun is extremely complicated and extremely interesting. There are all sorts of new phenomena that we cannot even measure on Earth that are involved there. The neutrinos are not only produced, but they're actually trapped in the core of a supernova for something on the order of several seconds. And this is the important time scale over which the explosion occurs and the energy is transferred. And those neutrinos are quantum entangled, just like in all the quantum information theory we're thinking about today. And yet they mix, their flavors mix while they're in these quantum entangled states. And all kinds of new phenomena associated with oscillations have been discovered. And I'm not sure we've actually fully resolved all things that could possibly happen in that kind of environment. It's frustrating because if that deep core physics did not exist, then the most immediate use of supernovae is that they have enough density that not only is the electron neutrino can become degenerate with the muon neutrino, but it could become degenerate with the tauon neutrino at still greater density. And this would allow us to actually order all three of the neutrino eigenstates. And that's a very big deal. It's one of the major goals of the Fermilab experiments that are being done today. But we could do that with astrophysics. The rub comes from the fact that we know this additional physics occurs in the core of the supernova that's nonlinear and highly complex, and we haven't solved that in a quantitative way yet that allows us to then use this flux of neutrinos as a nice calibrated source to do measurements in the outer mantle of the star.
Yeah, that's interesting. Okay, maybe I'll ask one more question. There's a few more, but let me just ask maybe one more question, then we'll let you go. Which is, let me try to. So the question was related to the Higgs and the implication for the Higgs in connection with neutrinos, and some people call the Higgs a God particle, and so it was referred to in the next question that way. Can you tell us? I mean, you touched on this a little bit, but just what does the mass of the fact that the neutrinos have a mass imply in relation to the role of the Higgs in a standard model, and also what does it imply for the standard model as a whole, and what are the possible solutions out there that are being proposed, and how we can reconcile everything moving forward?
Yeah, I think that the simplest way to think about it is the way that Hitoshi presents in that really cute slide, is that there's just this second mechanism that can generate mass among the neutrinos. So we haven't established that actually occurs. It could just be that the neutrino is just like the other fermions and a Dirac particle, and therefore it gets its mass from the Higgs. But that would leave us with this puzzle of then why is its mass so small compared to all the other fermions? So it's more attractive to think that nature uses everything she has. And she has not only the Higgs mechanism for the neutrinos, but she has this additional mechanism, the seesaw mechanism, that exploits the fact that the neutrino might have at least some component that is Majorana, some component where the neutrino is its own antiparticle. And so that does give this natural explanation for why we see this big gap between neutrino masses and the other masses of the fermions. So I would say it doesn't take away anything from the Higgs mechanism at all. In fact, it says that there's another really interesting way that nature can make masses, and that by putting the two together, the Higgs mechanism with this other second mechanism, that it can in fact explain one of the great puzzles in physics, why this huge mass gap between neutrino masses and other masses that we know about.
Yeah, well, I mean, I hope that people, what they get out of this talk is that, there's a lot of questions that have been answered, but many, many more yet to be answered. And I think Wick has given us a great insight in what an exciting field this is. And so I would encourage a lot of you to continue exploring and learning more about this. Maybe perhaps on that note, Wick, do you have any recommendations of books, either pop science or intro physics books that may touch on these topics for non-experts, or any resources in general?
There are some, and maybe what I should do is offline, I could send those to you. So you might post them somewhere.
Yeah, actually, some people ask for copies of your slides. I was going to ask you about that next. So maybe at the end, you can just put some references.
Yes. And if you like the history, and I love the history of this problem because it's so interesting and intersects so many different themes. There's a wonderful, it's an old article, but a wonderful article that was written sort of halfway through the solar neutrino problem by Davis and McCall that recounts the history, and that's worth reading as well.
Perfect. Yeah, I actually was going to ask you for personal reasons, any historical references that you might have. I think in physics, since we have to dive into so many topics, right? You kind of dive into it and forget a little bit of the historical context, and so even for me and many others, I'm sure it's useful to learn back about the history, even when you may know some of the physical phenomena to at least to some level. So yeah, if you could put that would be great.
Great.
All right. So I think with that, Wick, it's been a pleasure having you. Thank you so much. I really couldn't have thought of a better speaker to kick things off for the summer. For those of you that are going to be participating through the REYES summer program this summer, don't worry, we will be sending you updated information shortly. We will be having a meeting on Wednesday in 2 days from now, so make sure to join that. And whatever questions you may have, feel free to write to regis@odu.edu, and we'll get back to you whenever possible. Thanks again, Wick, for your time. Much appreciated, and I hope to see you soon.
Great. Thanks for all. It was fun. Bye, everyone.